Section 4.9, Antiderivatives. A function f, big F, is called an antiderivative of f, little f, on an interval I if f prime equals f for all x in the interval I. So what we're saying is you go backwards. If you have a function and its derivative is another function, then the original function that you were taking the derivative of to get to the new function is called an antiderivative of the new function. So if f is an antiderivative of f on interval I, the most general antiderivative is capital F of x plus c, where c is some arbitrary constant. This follows pretty quickly to the corollary to the mean value theorem we did. You might remember that we said that if a function f prime is the derivative of f, and we also have that g prime is the derivative of f, then we said that f prime and g prime had to differ by a constant. This was the theorem. This is the corollary to the mean value theorem that we proved in section 4.2. We said that g had to equal f of x plus c, which should make sense because if you take the derivative of both sides, you get g prime equals f prime. Derivative of the constant is just 0. So we can see that in general, if we take the derivative of any function plus a constant, the constant gets eliminated, we get the derivative that we wanted. So we can add anything to it. For example, if I had x squared and I want the derivative, that's 2x. But if I have x squared plus 10, the derivative is still 2x. X squared plus 10 plus, 11, x squared plus 21, derivative would still be 2x. So it doesn't matter what constant we add. If we want a general antiderivative, we have to just call this entire possibility a constant c in general, because it could equal anything, because who knows what was eliminated to get you back to 0. Let's do an example. Let's try finding the most general antiderivative of each of the following functions. So we'll start with f of x equals sine x. So we need a function whose derivative is sine. Well, the derivative of cosine is minus sine, right? So the derivative of minus cosine would equal sine. Derivative of the cosine part is minus sine, then the minus cancels. So this means that the most general antiderivative, capital F, will equal minus cosine plus some constant. Because when we take the derivative to test this thing, we get sine plus 0. So that works. Let's look at antiderivative of f of x equals 1 over x. Let's see, we know that the derivative of ln of x is 1 over x. So we could say, okay, the antiderivative of 1 over x is ln x plus c. But actually that's not the most general antiderivative, because this only applies to positive values of x. But remember, we have another function whose derivative is also 1 over x, and that's the absolute value of x when we take the natural log. ln absolute value of x also has a derivative of 1 over x. And that applies to a lot more x values. That applies to every possible x value that's not 0. So we can plug in negatives over there too. So that means that the most general antiderivative of 1 over x is, ln of absolute value of x plus c, which we can write as a piecewise function. ln x plus some constant, and ln of minus x plus some constant. In this case, it's if x is positive, and the other one if x is negative. However, this is still not completely general. There's no reason to think that these two constants have to be the same. So I could say that this is one constant, and then this is a second constant that's possibly different. So I make one of them C1 and one of them C2. Now that's the most general you could possibly be. Let's look at our power function, f of x equals x to the n, assuming that n is not minus 1, because if it was, then we would just be over there. So we need a derivative of something to be x to the n. Well, by the power rule, remember, you reduce the number each time. So you might think, okay, let's take the derivative of x to the n plus 1. because then it'll be reduced by 1 and give you xn. And that's true. If you take the derivative of xn plus 1, it will be reduced, and it will give you xn. However, you also have to multiply by the power when you're taking the derivative, so you would have n plus 1 times x to the n. And there's no n plus 1 in front over there. So we need to make sure that our function divides by n plus 1 so that it cancels when we take the derivative. Now notice, if I take the derivative of this guy, n plus 1 hops out, cancels with n plus 1 on the bottom, and then the power goes down by 1. So that's perfect. This derivative is equal to n plus 1 times x to the n over n plus 1, which cancels and leaves us x to the n. So that's our most general antiderivative. So now we have a way of finding antiderivatives of power functions in general. And our way is that we increase the power by 1 and divide by the new power, which should make sense because your power rule says first you multiply and then you subtract 1 for your exponent. So if you want to go backwards, first you should add 1 and then you should divide instead of multiply. So we add 1 and then divide instead of multiplying and subtracting. Let's find all functions g such that g prime is this. In other words, let's find the antiderivative of g prime. Okay, so let's simplify this a little bit. And by simplify, I mean let's split this up. So we'll write this as 4 times sine x plus 2x to the 5th over x minus square root of x over x. That becomes 4 times sine x plus 2x to the 4th minus 1 over x. Oh, let's convert that all to powers so that we can use our reverse power rule. So 4 sine x plus 2x to the 4th minus x to the minus 1/2. That means, well, we already got the antiderivative of sine. We said that's minus cosine. So this is 4 times minus cosine. And then 2x to the 4th. Well, x to the 4th, we increase the exponent and then divide. So it's going to be plus 2 times x to the 5th over 5. And then again, we increase the exponent by 1, so this becomes x to the 1 over 2, and then divide by 1/2. And we have our arbitrary constant. Simplifying, we get minus 4 times cosine plus 2/5 x to the 5th minus 2 rad x plus c. Let's find f if f prime is equal to e to the x plus 20 times 1 plus x squared to the minus 1, and f of 0 is minus 2. So let's start by writing out our derivative. We've got f prime equal to e to the x plus 20 times 1 over 1 plus x squared. Notice that we're not writing this as capital F, we're writing it as f prime just because they gave it to us that way. If they don't give it to us in general and we're looking at an antiderivative of f and that's what we're starting with, then we say that f will be the derivative and big F is the antiderivative. But if we're starting with the prime notation, then we just keep using whatever they gave us, and then the antiderivative will just be the f without the prime. Just like in the previous example where it was g without the prime. So taking the antiderivative, we get that f is equal to, well, let's see, e to the x. We could differentiate that a million times over. E to the x to be derivative, e to the x, e to the x, e to the x, e to the x. So antiderivative will also be e to the x. Because if I take the derivative, I get e to the x. 1 over 1 plus x squared is a little bit more obscure. Remember, that's the derivative of a function. It is derivative of inverse tangent. So this is plus 20 times tan inverse. Because if you take the derivative, you get e to the x, and you get 1 over 1 plus x squared. Let's look at f of 0. We'll plug in 0, we get e to the 0 plus 20 times tan inverse of 0 plus c. And we know that this has to equal minus 2, because f of 0 is minus 2. Okay, e to the 0 is 1. Tan inverse of 0, well, that's when sine is 0, which is 0. So this implies that our constant is equal to minus 2 minus the e to the 0 is 1, so it equals minus 3. So now we have our particular function for this example, a to the x plus 20 tan inverse x. Instead of plus c, we know what c is, so it's minus 3. Let's find f if f double prime is 12x squared plus 6x minus 4, f of 0 is 4, and f of 1 is 1. Notice in the previous example we had f prime, so they only gave us one y value. And in this example we have f double prime, so we need 2 in order to solve for this thing uniquely. So let's start with our derivative, f prime. Remember, that's the antiderivative of f double prime, because its derivative is f double prime. So that's 12 times, well, instead of x squared, it'll be x cubed. We increase the power by 1 and divide by our new power. So plus 6 times x squared over 2 minus 4 times, well, let's see, the derivative of something to get 4, there would have to be an x there. If we take the derivative, we lose the x and just get 4. And we have our arbitrary constant. Simplifying, we get 4x cubed plus 3x squared minus 4x plus c. Taking another antiderivative, we get 4 times x to the 4th over 4 plus 3 times x to the 3rd over 3 minus 4 times x squared over 2 plus, well, when you take the antiderivative of a constant like this one, you just add an x. So when we take the antiderivative of c, we'll keep c and just throw an x in there. However, we just took an antiderivative, so it's possible that there was some other constant, let's say d. If you take the derivative of this, well, all of these, it's pretty clear that they work out via the power rule to give you all of these. And similarly, if you take the derivative of this guy, it's a constant times x, so it leaves you with just a constant. And then taking the derivative of this guy just leaves you with 0. Simplifying, we get that this equals x to the 4th plus x to the 3rd minus 2x squared plus cx plus d. So now let's use our f of 0. They told us f of 0 was 4, but if we plug in 0, this is gone, this is gone, this is gone, this is gone, so we just get 0 plus d. That must equal 4, because f of 0 is 4. Okay, so that means that d must equal 4. So now we have one of the constants solved for. Let's use our other y value to get the other constant. F of 1, they said, was 1. Well, if we plug in 1 for each of these guys, then we get 1 plus 1 minus 2 plus c times 1, which is c, plus d, but we said d was 4. And we know that that has to equal f of 1, which is 1. Okay, solving for c, this implies that c is equal to minus 3. So now we have our function f. F must be equal to x to the fourth plus x cubed minus 2x squared minus 3 times x, because c was minus 3, plus 4 because d was plus 4. Okay, say we have the graph of a function f. Let's see if we could find an antiderivative graph. Well, we're given that big F of 0 is 2. So how about we start there? So that's 2. That could be our first point. Why not? Then it looks like from 0 to 1, our derivative is negative. If our derivative is negative, it's underneath the x-axis, then that means our function is going down. So up until 1, our function is decreasing. If we go from 1 to 3, then our derivative is positive. So whenever our derivative is above the x-axis, that means our function is increasing. So we should be going up until we hit, let's see, what is this, 2 and then 3. And then it looks like we should start going down. So let me erase this a little bit, because we should start going down once we hit 3. So it looks like I should stay up there a little bit more, and then, and then maybe start going down once we hit 3. Let's see if I can put these in first. Maybe it'll be easier to draw. Okay, and then from 3 on, it's negative. So it should be decreasing forevermore. But see how it gets closer and closer to 0? So it gets less and less negative. So our function kind of levels off towards the end. And over here was 1. This looks like it's probably pretty good. We could even confirm this by taking a look at the second derivative. If we look over here at these tangent lines, you can see that the slope of the tangent line goes from positive to negative. So that means the second derivative changes from positive to negative over here. So it looks like we have an inflection point over here and an inflection point over here, which makes sense. We have inflection points over here and inflection points over here. So it looks like this is a pretty good graph for our antiderivative. A particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6 centimeters per second, and its initial displacement is s of 0 equals 9 centimeters. Let's find its position function, s of t. Okay, let's start with the acceleration. Remember, acceleration is the derivative of velocity. So v prime of t is a of t. And they told us that that's 6t plus 4. So since we're starting with a derivative, we can get back to velocity by doing an antiderivative. So we could say that the velocity is the antiderivative of acceleration. So that's 6 times t squared over 2. Increase the power, divide by it, plus 4t plus c, which simplifies to 3t squared plus 4t plus c. Well, it would be great if we knew what the c was. It turns out we can know, though. They told us that v of 0 was minus 6. So let's use that information. V of 0, well, if I plug in 0, this is 0, this is 0. So I'm left with only c. So I get that v of 0 is c, and I know that that equals minus 6 because v of 0 is minus 6. So now I know that c is minus 6. Okay, great. I can rewrite v of t now, getting rid of that constant because I know exactly what that constant is. I can replace it with minus 6. So I have 3t squared plus 4t minus 6. In the same way that we started with acceleration, because that's the derivative of velocity, we can now start with the derivative of position, because velocity is the derivative of position. So taking the antiderivative of velocity will give us the position function. So that's 3 times t cubed over 3 plus 4 times t squared over 2 minus 6t plus another constant. We already used c, so let's use d. Simplifying, we get t cubed plus 2t squared minus 6t plus d. So let's use the fact that s of 0, they told us, was 9. So s of 0, if we plug in 0, this is gone, this is gone, this is gone. We just have d. So that must be equal to 9, so that means that d must be equal to 9. So now we know what our constant is. S of t must be equal to t cubed plus 2t squared minus 6t plus 9. And that's our position function. Say a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Let's find its height above the ground t seconds later. When does it reach its maximum height? When does it hit the ground? In order to do this, we'll assume that downward acceleration g is constant, and its value is about 9.8 meters per second squared, or 32 feet per second squared. Okay, we want to find its height above the ground. So we want to find the position function. Let's assume that going up is positive and going down is negative. So that means that if we start with our acceleration function, a of t, that's the derivative of velocity with respect to time, and that'll be minus 32 because it's accelerating downward at 32 feet per second squared. Let's antiderive this to get velocity. So v of d would have to be minus 32 times t plus some constant. But we know that the initial velocity, it said, was 48 feet per second because that was our upward speed that the ball was thrown at. So that means that if we plug in 0 over here, we get 0 plus c would have to be equal to 48. So now we know that c is 48. So we can rewrite our velocity function without the arbitrary constant and with the specific constant of 48. This tells us what our maximum height is. The maximum height would have to be when the velocity is 0, right? That's when we have a maximum. Because velocity is the derivative of position. So when the derivative is 0, that's when you have a maximum. When the velocity is 0, that tells us that t would have to be 1.5 seconds. Let's do another antiderivative now. Let's get position. So that'll be the antiderivative of velocity, so that's minus 16t squared, because it's t squared over 2, and then half times 32 is minus 16, so plus 48t. And a new constant, d. Again, they gave us an initial value. They told us that it's thrown upward from the edge of the cliff 432 feet above the ground. So that means that if we plug in 0, 0 plus d must be equal to 432. So that means d must be 432. So now we have our position function all filled in. Minus 16t squared plus 48t plus 432. Well, the ball hits the ground when the y value is 0, so that's when the position function is 0. So S of t needs to equal 0 for this thing to hit the ground. Let's see if we can figure out what t is. Okay, we have minus 16 t squared plus 48t plus 432. I want to know when that equals 0. We can divide by minus 16 and get that this is t squared minus 3t minus 27 equal to 0. So they both have the same root. So now we'll use the quadratic formula. So t is going to be equal to 3 plus or minus the square root of 3 times radical 13 over 2. So that's when the ball hits the ground. Ball will hit the ground after 3 times 1 plus rad 13 over 2 seconds, which is about 6.9 seconds. Notice we reject that negative value because we're not time travelers.